esteemed participants and distinguished guests. Welcome to this international webinar on strategic research project management, quantum dot synthesis, properties and applications for a bright future in solar energy harvesting. It is a pleasure to be a part of this collaborative initiative by the Research and Development Cell, Internal Quality Assurance Cell, Department of Chemistry of St. Joseph Vaz College, Goa, India, in partnership with the Applied Acoustic Research Institute, Dubna, Russia. St. Joseph Vaz College is an undergraduate college established in 2017. It is named after St. Joseph Vaz, who was an educator par excellence, who inspired many as an exemplary teacher. It is affiliated to Goa University and offers courses in subjects such as chemistry, botany, microbiology, and mathematics. On the other hand, the Research Institute of Applied Acoustics was established in 1994 with the primary objective of conducting scientific research in the field of acoustics and hydroacoustics. Its main focus is to develop and implement technical means for modeling acoustic fields and measuring parameters, creating acoustic stands and use them to study acoustic vibrations in the surface layer of the atmosphere and test the effect of acoustic vibrations on rocket equipment. I sincerely thank all the organizers, presenters, and participants for their commitment to fostering collaborative research. May this webinar be a catalyst for new insights, meaningful discussions, and lasting collaborations that contribute to a brighter and sustainable future in solar energy. Thank you, and I wish everyone a fruitful and enlightening experience throughout this international webinar. Thank you.
Thank you.
About our resource person, scientist Mr. Dezev Sergey is a Russian scientist from the Applied Acoustic Research Institute, Russian Federation, Duba, Moscow. Sir has done his qualification in 1996-2001, Specialist Chemistry from the State University Research, Russian Federation. Sir has completed up graduation in Bioorganic Chemistry from the Institute of Bioorganic Chemistry, Russian Federation, year 2001-2004. The area of interest: quantum dots, nanotechnology, colloidal organic polymer chemistry, bioconjugate, unique optical material, solar energy, and etc. Sir has done several publications in international journal with having the highest impact factor. In and around, Sir has published more than 15 research papers in international journals. Some of them are evaluation of effect of quantum dot, bioconjugate based on the terms of prospects for the treatment of resistance, the International Journal of Chemistry in 2021. Synthesis of highly photostable emitting quantum dots, nanotechnology in year 2016. Colloidal quantum dots for fluorescent labels of proteins in Material Science and Engineering Journal. Sir has also have few patents registered on his name. The one is luminescent ink for the cryptographic protection of documents and articles from falsification. The second one is method for obtaining a multiplex diagnostica. We are truly honored to have you, sir, here with us today, and we are eager to learn more from your experience. Without wasting time further, let's welcome Sir Dezev Sergey to our online virtual session. Over to you, sir.
Thank you, Melvin. I want to say hello for everybody from cold Russia. I'm really glad to take part in your webinar, and I want to show you my presentation. And the main goal of my presentation, it's my best wishes for you to find your own way how to harvest solar energy. Your climate in India, in Goa, is very sunny and stable. So you have a lot of such type of irradiation energy, and you can find a way to how to collect it's more effective and more costly. Because modern nanotechnologies right now, they can help you in your bright future. So I will start my presentation, okay? So my presentation, quantum dots, synthesis, properties and application for bright future in solar energy harvesting. My name is Sergey Dezhurov. I'm from Russia, from Dubna. Dubna is part of Moscow region at the north of our region. I'm from Applied Acoustic Research Institute. This is institute, one of the institutes, and we are part of a group with collaboration with Dubna University. In our town we have State University Dubna, and two people we have like our staff. It's Gladyshev Pavel and Krylsky Dmitry. Right now they are on a pension, and so that's a reason to find some colleagues to help me with producing quantum dots and involve this part of chemistry into your life. Some words about our science city Dubna. We have Dubna University, Joint Institute of Nuclear Research. You know, nuclear research is one of the famous investigation in Russia, like nuclear bombs and atom energy. And also my own institute, Applied Acoustic Research. This is our office in the center of the town, and also we have a big fabric zone, a big science zone outside the city. Actually, acoustic research is a historical name because it was started from hydroacoustic on our sea. But right now we have a lot of our projects that not connected with real acoustic. This is our Dubna State University. We have a lot of students who make them diplomas in with the help of our science institutes. And our biggest joint institutes of nuclear research, it's, if you know, biggest institute in Europe. It have a deal with nuclear research, and the new elements of periodic table of Mendeleev coming from this institute. So right now I want to tell you about quantum dots, their properties and synthesis. Quantum dots are part of nanomaterials. Nanomaterials is microscopic particles of inorganic material like semiconductor, cadmium selenide, zinc sulfide, silicium, and some other types, or that nanoparticle is like organic style, polymer, protein, viruses. Nanotechnology means that particle size is less one micrometer or 1000 nanometers. Biggest part of these nanoparticles is quantum dots. This is semiconductor nanoparticles that exhibit quantum confinement, and their size is typically less than 10 nanometers in diameter. So what about quantum confinement? Quantum confinement is interesting effect that appears when your particle have diameter from 2 to 10 nanometers. At these sizes, we have a special effect. Our energy levels, they are quantum confinement, and they are changed from biggest size to small sizes. These energy levels becomes wider. In bulk structure, there is no any quantum confinement, so you can't see any luminescence from bulk semiconductors, not like from quantum dots, because these discrete levels of energy, they produce a strong line of fluorescence in part of the spectrum that's connected with the size of these nanoparticles. The biggest particles are more red, and the small particles are blue. Typical construction of quantum dots, it is a core, semiconductor core, semiconductor shell, and additional shell or shell with ligands on the surface. These ligands, they do possible to disperse these nanoparticles in such matrices what you like. Such solvents, you can use any solvent from water to chloroform, dioxane, and other types like acrylic monomers, and a lot of other things. So ligands, they help you to disperse these nanoparticles in a media. About properties of quantum dots with comparison with organic fluorophores. First, it's high quantum yields. Right now, there are samples, it's near 1 unit, it's 100% of quantum yield. And respect to the high absorptivity, they are about 20 times more brighter than organic fluorophores. Also, they have narrower and more symmetric emission spectra that think you can use to convert energy to preferable wavelength. And third is one of important thing, the properties of quantum dots. It's very good stability to photo bleaching. It's about 100 to 1,000 times more stable than any organic luminophores, because they easily photooxidate by oxygen from atmosphere, and after destruction, photobleaching has happened. The fourth property is a high resistance to photo and chemical degradation. The same oxygen or other active spaces, they couldn't affect quantum dots if you create a good Lagrange, a good shell for your quantum dot. The fifth is tunable wavelength. The range is very big, from deep ultraviolet, from 100 nanometers to 4 micrometers. It depends on composition and size of a quantum dot. For synthesis of such quantum dots, we use some lab equipment, and I want to tell you about our lab. We have reactor, chemical reactor, that possible use it with the high temperatures, more than 300 degrees, and you see this all automatized, and it's possible to use inert gases, vacuum, and other types of media inside. After synthesis, we need to clean our product, and we use centrifuge for these needs, and for clean our solvents and to separate the media, we use a vacuum evaporation with rotational evaporator. Also, we use spectral equipment like a spectrofluorimeter and a spectrophotometer. And right now, about process of synthesis of colloidal quantum dots. Here you can see a setup that consists of three neck flask. One flask is used to inert gas like argon, thermocontroller, and the third neck is used for syringe to take some probes from here. And there are two types of processes: heating up and hot injection. Heating up process, it's like you use all precursors before heating, and after that your temperature go up and process is start. Other way is hot injection. When you first use one precursor here and other precursor you inject after temperature rise to 200-300 degrees of Celsius. And in the literature you can see microfluidic type of reactors. It's flow reactors. They can produce different types of quantum dots, but not everything, because classic reaction is more powerful technically. About kinetic of formation of quantum dots. First, you have a mixture of precursors like metal and halcogenide like sulfur or selenium. First stage is creation of molecular intermediates and clusters, very small creations. This process is depends on temperature and concentration of your precursors. Obviously, it's happened at temperatures from 200 to 300 degrees. And at less temperatures and with less energy, nanocrystals grow up. Nanocrystals growing, it depends on the time and temperature. Time and temperature, after you control these parameters, you obtain nanocrystals with properly size and use them for next steps. About the practical application of quantum dots. First famous application is light emitting diodes. For example, QD LED TVs on the market, you can buy it, no problem. Second one is the goal of my presentation. It's about solar energy, it's light concentrators and elements of solar panels. Third one is biological use. We have some researchers for diagnostic and visualization of different pathogens, viruses, bacteria. We have experience in creation of test strips for testing any pathogens in biological fluids. Also, quantum dots applicable in security and technical labeling, tracers for oil and gas. But we will talk about one of the favorite application. It's quantum dots for solar cells applications. There are two types of technical schemes how you can use quantum dots for solar cells. First way is using as a part of luminescent solar concentrators. Advantages of this technology is simplicity and proven stability, because we have samples right now that older than 15 years right now, and they still works. And what about the second way? It's using as a part of photovoltaic device, PV cells. Advantages of this technology is relative cheapness, and maybe it will be perspective in future, but right now it still in research. When luminescent solar concentrators, they have companies and some startups right now on the market. The one of the simple and proven technology using quantum dots is luminescent solar concentrator. The basic design of such concentrators is a transparent plate doped with luminescent material, and it's able to absorb sunlight, and it guides photon and produced a light edge with a spectra what you like, and sunlight concentrate on this edge, and you can use this transformed light in original PV cells, like you can see at this gem. On the edges, you using solar cells, and your square of luminescent concentrator put all solar light to the edges, or a lot of solar light to the edges when you are using a solar cell with a small square. So this is concentration of solar light by using thin films and like glasses, like films on glasses technologies. And right now it's proven about 10 to 20% of efficiency of solar panels, and not only increasing of efficiency, also a shelf life of these solar cells will be greater, more than 10 years more, because the worst thing for solar panels is radiation and ultraviolet and Röntgen radiation. They destruct the solar panels, and they shelf life it's not extended too much to use them efficiently. So right now there are a lot of startups with such kind of technology. One of these startups, they're using Windows, and they create a thin film on the surface of this window, and this window becomes a solar concentrator. Sorry. Other way using of quantum dots is like a part of a PV cell. In solar cells based on quantum dots, nanocrystal use metal halcogenides, which have semiconducting properties such as cadmium sulfide, cadmium selenide, lead sulfide, and lead selenide. Under the influence of light, materials such as charge separation occurs, pairing electron hole, and you can watch a video about this theory. I have a link in my presentation. This technology is also very, very interesting, but it needs a lot of experience with different type of technologies, and good experience in microscopy, because you need to understand how particles are applied on your device, and this is more complicated technology than using luminescent solar cells. But this technology, it's easy to apply in a roll system, and this kind of technology is very cheap. But it's still a challenge, because stability of such films still unknown. Still on research. And here you can see a progress in quantum dot photovoltaic cells. From 2008 to 2020, it's go up from 2% of efficiency to 16% of efficiency, and it's possible will grow to 20 and more percent in several years. So about this PCEs, photovoltaic cells, described largely to the introduction of three main QD solar cell architectures. The first is Schottky. Next is the plate heterojunction, and third is NIP. This device engineered breakthrough have been further augmented along the way with robust service passivation, receive and deploying of SSE and later SPE. You can see that
49 झालं
very
माझी
fast
exam.
growing of these technologies, and one of the best they are made on lead sulfide and on a perovskite quantum dots. So this is interesting field of technology, and maybe if we start from simple things, from simple synthesis of quantum dots, right now it's enough simple for students and at schools. It's very easy, and we can build a base for this technology with your help and in your place as you wish. And thank you for your attention. Question, please.
40 minutes अभी तो कहाँ पर
Hello. Melvin. Well, thank you very much. And if you have any questions, I will try to answer.
So my question is like solar energies are like renewable and very environment friendly sources of energy. Like so, when we come to like quantum dots for the preparation of like for effective solar energy use, we use some heavy materials like lead and cadmium, like toxic materials for environmental hazard and all. So which contradicts are like used in the solar cells and all, like for the prepare like for a for a renewable source or like efficient source of energy and all. What do you consider for that? Like
Yes, I understand your question. So yes, a lot of materials, quantum dots, they have heavy metals like cadmium, like lead, and you should understand this thing, yes, but it's less than in batteries or accumulators. What are you using in your cars and in your toys? It's very small quantity. And second thing is matrix. When you are using proper matrix for these nanomaterials, they are stable in their solid state, and no salvation, no elimination from this film possible. You can utilize them like accumulators with lead, with a plumbo, the same style. It's not a great problem, but actually we have quantum dots without any heavy metals. It's indium phosphide quantum dots. They contain only indium, zinc, and that's all. Thank you.
yeah, like same so with in medical field also, like they are like mostly like quantum technology is used for detection of like some cancerous cells and all, like tumors and treatment and all. So like this using of this like heavy metals and all like can be critical like or dangerous for the patient and all if something goes wrong.
Yes, you can't use any cadmium quantum dots for treatment, but you can use them in analytic instruments only in special test tubes that are not possible to destroy and eliminate any heavy metals from there. It's just part of technology when you using and utilize these parts the right way. It's only a question of organization of this process, because in Russia we collect all old batteries with cadmium and utilize it different from other parts of our garbage. It's part of politics question, I think, only like this. And also you can use cadmium-free quantum dots as well as indium phosphide.
Thank you, sir, for your explanation and all.
Now I call upon Miss Angela Serra to propose a word of thanks.
Okay.
Good afternoon. It is with great pleasure and sincere gratitude that I stand before you to express heartfelt thanks on behalf of St. Joseph's College for your participation in our enlightening webinar that has truly transcended borders. First and foremost, our deepest appreciation goes to our esteemed speaker who has generously shared his knowledge, insights, and expertise on the topic quantum dots synthesis, properties, and applications for a bright future in solar energy harvesting. Your perspectives have not only broadened our understanding, but have also inspired us to think globally. It is with immense gratitude and privilege that I extend my sincere thanks to our respected administrator, Professor Simao Denise, and our principal, Professor AAR Maria Fonseca, for their unwavering support and foresight in allowing us to organize and conduct this international webinar that has truly exceeded our expectations. A special word of thanks goes out to our collaborators, Applied Acoustic Research Institute, Dubna, Russia, for their support. Your commitment has been instrumental in making this event a great success, and we truly appreciate the faith you have shown in our vision. A profound thank you to our attendees from around the world. Your active participation and thoughtful questions and diverse perspectives have contributed to the richness of the discussions and made this webinar a global forum for the exchange of ideas. Your presence has turned this virtual gathering into a vibrant and dynamic intellectual space. Behind the scenes, a special acknowledgement goes to the hardworking technical team and organizers who have worked tirelessly to ensure the seamless execution of this international webinar. Your dedication and attention to detail have been instrumental in creating a smooth and engaging virtual experience for our participants. As we bring this international webinar to a close, let us carry the knowledge and connections we've gained forward, fostering continued collaboration and understanding across borders. Once again, thank you to the speaker, attendees, management, and organizers who have contributed to the success of this international webinar. Your collective efforts have made this event a valuable platform for global exchange. We look forward to future opportunities to connect and learn together. Thank you and have a wonderful day.